you got a big tool, it's alright.
That's what she said.
Don't try to do that with a 1/8" cutter or something, you're going to break it. That's more than, yeah, that would mean like 1 revolution. Yeah, no, that's not going to work. So the chip load varies between the size of the tool usually. So you'll see that a lot in the charts. If it's a smaller tool, it's going to have a much smaller chip load. Like if I'm using a 30 seconds tool, I might not even use 1,000. It might even be a 1/2,000 chip load. But you got to remember that thing's spinning a lot faster too.
So you can cut a lot. The feed could be a lot faster with a smaller chip load.
No, the higher chip load means your feed goes up. Because what's the formula for feed rate?
I lost my paper in that computer lab.
Feet per revolution?
No, feed inches per minute. It's the number of teeth, right? Number of teeth times the chip load times the speed, right? I don't know if it's in that order on whatever you're looking at, but that's usually what it is. So that means if my chip load increases, they're all multiplied, right? So that means my feed must increase.
So IPM is your...
Inches per minute is your feed rate. That's how fast you're feeding into the material. Okay. We'll get to that. So surface feed per minute. What are we talking about here? What's the surface feed per minute? You guys remember where I was talking about the cars going down the highway?
Yeah, I was not here for that one.
So if I'm driving my car, right, I'm going 60 miles per hour. My wheels in my car are spinning, right?
Is your car shaking?
Usually going twice
No.
as fast.
No.
Say my wheels in my car are, I don't know, this big. There's the wheels in my car, right? And I'm going 60 miles per hour, right? And right beside me is a big old semi-truck. He's got a huge wheel, right?
Well, that's like totally disproportional.
And he's going 60 miles per hour too.
It's like a...
But he's
And then
getting
I'm
more
done.
surface. He's getting more surface feed.
No, he's getting the same surface speed. We're going the same speed,
Oh.
right? And then I got this little smart car behind me. Yeah? It's this big, right? But it's still going 60 miles per hour, right? So this is what we're worried about. We're worried about how fast are you actually moving across the surface. So 60 miles per hour, that'd be what, 5,280 surface feet per minute? Which is ridiculous. You would never cut anything that fast, for sure. But what's that mean about the rotational speeds of these?
Unless you were cutting stuff on the highway with concrete.
What's the rotational speeds of these? They're all going to be rotating at the same speed or not?
No, because there's different radius.
So which one's going to be going the fastest?
Small.
This one, right? This one's going to be spinning real fast. Right? This one's going to be going really slow, right? And your car's going to be somewhere in the middle. Right? So the surface speed per minute is just telling us how fast is that tooth, that single tooth, just think of one tooth, moving across the surface. Right? So think about it this way. If I move something really quick across the surface versus really slow, which is going to create more heat? Fast, right? So your surface speed controls your heat and your cutting, really. That's what you're talking about, is how much heat is there. So,
Going back to that first equation, what's LL for again?
we'll get to that. Don't worry about it. We'll get to that.
Okay.
So every cutter has a diameter, right? So that's our car wheels over there. We have 3 different diameters. And you multiply that by the circumference, you get the distance it travels. So we're talking about the rotational now. And the surface speed per minute is just how far the cutter edge travels in 1 minute. So you're thinking about that cutter edge traveling a linear velocity in 1 minute. And that's what the surface speed per minute is. And you'll see on the chart anywhere from 20 surface feet per minute all the way up to 3,000 for some crazy materials. Yeah.
Are we taking a break anytime soon?
Yeah, after we finish this. Then it'll be the last time.
Sorry.
So, just remember to think about that as how fast one tooth is moving across the surface. Just think of it that way. It's easy to remember.
It's okay. So when it's on the lathe,
Yeah.
that tooth, it's actually dependent on how big the diameter is of whatever you're cutting.
Exactly.
Okay, so I kept thinking it has to do only with the tooth, that's why. I was
No, it
confused.
has to do with whatever's rotating.
Okay.
Like that.
Fuck. That was scary. Thought the school was getting blowed up.
So, what's service speed per minute? It's the speed that your tool is moving across the material. So if you were to think of it as like a chisel, like I just got a chisel and I'm chiseling something, if I take that chisel and go fast, or if I go slow, that's what your service speed is. So the faster you go, the more heat you have, right? The slower you go, you have a little less heat. So if you look at this chart here, it's kind of hard to see, it's small, I get it, but
That would have been nice.
you have your service speed per minute right here. It's going from 10 all the way to 1200, 2000, right? So 10 to 2000, and across the top you have diameters. And what you see happening here is like at 10 service speed per minute, depending on the diameter, your RPMs get changed, right? So if I'm using an 8-inch tool at 10 service speed per minute, it's going to be 305 rotations per minute, right? But if I go up to a 1-inch, it's only going to be 38. So the tool diameter has a lot to do with how fast you're spinning your tool.
So on the outside, it's not gonna be going as fast as if it were on the inside, surface-wise.
Yeah.
Okay.
So that brings us to spindle speed, which is the RPM of your machine. So the RPM of the bridge port, the actual tool spinning, or the RPM of your lathe piece spinning towards you or away from you. And that is your service speed per minute times this constant. They spent millions of dollars trying to figure out what this constant is, and then you divide that by B.
And
Is that the 3.189?
Yeah, they just rounded 3.82.
so we got 700.
It's fine if you use
Yeah.
3.82. You're not going to be off by that much. Just don't use 3.8 because that 0.2 can make a pretty big
Yeah.
difference by some amount.
Hopefully. I was trying to
At least
read
got
into
number one right.
I was trying to read into that damn thing too hard. Too much, man.
So, like, let's do an example here. We want to cut some aluminum. And the cutting speed we looked up in the chart for our tool was 900 surface feet per minute. Okay? And let's say we're using a half-inch cutter, half-inch tool. So all you do, just plug it in. So 900 times 3.82 divided by 0.5. And that should give you your RPM. What is that?
$68.76.
68.76.
That's all I got.
900 times 3.82 divided by 0.5. What'd you say?
68.76.
Oh, I thought you said 68,000 or something.
No.
Yeah, that's the same.
Yeah, so that means it needs to be spinning 6,800 roughly RPM, right? No machine in this class can do that.
We were just talking about hooking up a car to the lathe motor.
I've seen people do that actually.
Really?
Yeah, I've seen people I've seen it like down in Kentucky. Like people,
Only in Kentucky.
Only in Kentucky. But they'll take their lug nuts and they'll bolt on like pieces of wood. And
Wood?
Yeah, they'll make like art out of it. I've seen it. It's pretty crazy
So
stuff.
they just
Very
bolt
dangerous.
something to their wheel and turn the car on.
Yeah, basically they had their car on blocks. They took off their wheel They bolted a piece of wood on there,
I'm gonna try that.
cranked
That's
that thing up
awesome.
with the gas, and they had like a bar in the ground, and it was like a lathe basically.
Yeah.
And they were like making bowls and lampshades and all kinds of stuff. So
With wood or?
with wood,
Yeah.
yeah. So here's our RPM right there. So that means I gotta run the Bridgeport at that fast if I want 900 surface feet per minute, right? Obviously, we're not cutting at 900 surface feet per minute back there. Not with a 1/2 inch tool, at least, right? So let's upgrade this to a, let's say it's a 1.75. What's that going to come out to?
1964?
0.5.
Yeah. Wait.
Don't, we can't do the 0.5.
19,
We'll put it there, but.
1965 then.
So you can see how much that dropped now. Huge amount. And that's because our tool got bigger. So that means the outside spinning.
It's slower.
Yeah, the tool got bigger. So the outside, we want that to spin at the same speed, right? So that means we got to spin slower. And that's, what is that? That's a huge amount smaller.
So even if the whole thing, let's say, is
So you get 26% or 7.
It's actually a factor of 3.5. It's 3.5 times smaller. So.
Or like 25% of the number. Well, yeah.
No, it'd be like
Back-
350%, right?
you
I'm
said
looking at
3 point
I'm looking at it
Yeah.
backwards.
Yeah, 350%.
That's
So-
right. You're right.
If you're back on the Bridgeport and that thing only spins at 4,000 RPM, or not even that probably, it probably spins at 3 something, and you want to get a high service speed per minute, you should probably use a bigger tool, right? That'd be a quick and dirty way to do it. So if I'm on the lathe, what's different about this?
Not the tool, but how big the piece of.
How big the piece of stock is, right?
Yeah.
So if I'm cutting something 1.75 inch, I'm good to go. I can run the lathe at that speed, no problem, right? And I'd be cutting 900 service feet per minute.
So people actually measure this stuff out, they don't just throw it on there.
On a manual mill, most people just throw it on there and go. Because you don't really need to, you can feel it. You can hear it, you can see it, it's easy to adjust. Nobody really calculates, I mean, guys who run manual mills know this stuff by heart. I never calculated speed to feed for a manual mill unless it was something really important. CNC though, it's crucial. You gotta be perfect. You gotta be like right on or your parts are gonna turn out like crap. So that's why this is important. Because we're gonna start doing CNC right after welding. So
What are we doing welding?
welding's next week.
Cool.
So these are the only two variables you have here, the cutter diameter and the surface feet per minute. So basically the surface feet per minute only changes the RPM. That's all it deals with. So you cut something at a higher surface feet per minute, you got a higher RPM, we're talking about more heat, right? This is how we control our heat basically in our cut. That's what it's all about. And where do we want that heat to go? In the chip, right? You don't want that heat to go in the tool. You don't want that heat to go in the part. You want it to be ejected into the chip. And if you're going too fast, that heat won't eject in that chip. The heat will be stuck in the material, it'll be stuck in the tool, something will break, right? If you're going too slow, usually the problem is the heat is ejected quickly enough that the tool will start rubbing. And it's bad for tool life, really, if you're cutting way too slow. But that depends on your feed rate as well. So you can usually get away with cutting too slow, but it's not recommended. Like a lot of guys who are very new to machining, they're like, oh, I'll run really slow, and I should be fine, but then they break their tools. So feed rate, we're talking about inches per minute here usually. In the metric system, if you're cutting something, it's usually millimeters. Sometimes you'll see it in centimeters. It depends on the machine. And what this is the feed per tooth times the number of teeth times the RPM. So you can see right away that the RPM has a huge effect on your feed rate. They're linked very closely. And the ratio between them is very important. So like if I bump up my feed rate, or if I bump up my speed for some reason.